even from different countries to Zurich today for this workshop, so I'm really happy here. We tried to put together a very diverse program, so we really tried to cover the entire field of software reliability and correctness. So we will have talks about program specification and verification. We will cover dynamic and static analysis. We will have type systems, and we will have a talk that will tell us why we shouldn't have type systems. We will have synthesis, we have constraint solving, we have a talk about completely new ways of constructing software in the first place. So we really try to put together people that cover more or less the entire range of topics, which I think will make a good opportunity for interesting discussions. The program in that respect is in no particular order, so it's more or less random. And I also need to announce some changes to the program that you got as a hard copy, and they all affect this afternoon. So unfortunately, Ross is sick, so he's actually in Zurich, but too sick to give a talk. So John Boyland agreed to move his talk from tomorrow afternoon to today after lunch. So we will stop 45 minutes earlier tomorrow afternoon and instead have the talk today. Thank you very much, John, for doing that. And we swapped the talks of Jan Witek and Andrei Rybalchenko. So the session after lunch will be John and Andrei, right? And Jan will talk in the last session. Okay, there are a few things that I should announce before we get started. In terms of infrastructure, what you need to know is you have access to the public wireless here at ETH, so the SSID is public. The login is WSCR, Workshop on Software Correctness and Reliability, and the password is 2013. So that gives you a chance to go online. I hope you're not going to use it too much and instead pay attention to what our speakers have to say. But I know it's, of course, important to be connected. We do have student volunteers here. Maybe the student volunteers can get up. So there are the two people at the registration desk, and there's Andre over there. So if you have any problems, feel free to contact them, and they will try to help you. Also with questions like we already had this morning, where can I get coffee? I need some quick. Where are extra restrooms? Questions like that. Speaking of restrooms, they are behind the speakers, and there are not many of them. So you might want to use, at least in the lunch breaks and so on, also the facilities in the main building of ETH. Finally, coffee and lunch will be served in this room. However, if you want to go somewhere else, or if you look for dinner options, we gave you, as part of the paper that you got, a bunch of suggestions. So here's a map. We are here, and all of the suggestions are basically north of us, most of them up the hill here, and all of them will be quick enough in case you prefer going to a restaurant for lunch instead of staying here, and all of them are also decent dinner options. And one other thing that I wanted to mention is that we are recording the presentations here, and we will make the presentations available on the conference, on the workshop website after the workshop, provided that all the speakers agree to having their talks there. So you have a chance to look up the details again, even after the workshop. So with that, I would like to thank our speakers for coming here, and I look forward to the workshop. And now I'm handing over to Martin, who's going to introduce the speakers of the first session.
Including the Nobel Prize, and currently he's the editor-in-chief of the communication of the ACM, which I think has improved drastically. So, please.
Thank you. I'm happy to open this workshop, and I will try to give you a very quick story of the last 100 years. So we're going to start about 100 years ago, 1915. Leopold Lowenheim is studying the monadic class. The monadic class is the fragment of first-order logic, where all the predicates, with the exception of equality, are monadic, one place, unary predicates. Now, today it may seem very restricted, but you have to remember that for about 2,500 years of logic, going back to the Aristotelian syllogism, that's what people thought logic was. Only late in the 19th century, binary and higher order predicates were introduced. So Lovenheim studied first-order logic with monadic predicates only, and he proved the fair decidability results in logic. And I'll focus on the satisfiability problem. He proved a fundamental theorem that if a sentence is satisfiable, then there is a model whose size is bounded as a function of the size of the sentence. And you do it via quantifier elimination. So you reduce it essentially to propositional logic by eliminating quantifier, and the elimination causes the blow-up that we get. But this is very important because we still to this very day use this as a very fundamental decidability technique, both bounded model property and quantifier elimination. And later on, a few years later, Skolem showed that even if you go to second-order logic and you allow quantifying over monadic predicate, you still retain decidability. And you do sneak in one, as I said, one binary predicate, which is the equality predicate. And so you can ask, what happens if we go a little bit beyond equality? What about inequalities? And this had to wait about 40 years before people asked this question. And that question was asked partly as discovering a connection between automata theory and logic. So let me very quickly remind you kind of very classical automata theory, non-deterministic finite automata, which you should all remember, hopefully, from college. So it's a classical model in computer science where you have a finite alphabet, a finite set of states, set of initial states, a non-deterministic transition function that given a state and a letter, it gives you a set of possible successor state. You get a set of possible successor state and a set of accepting states, and you feed it a finite sequence of letters. An automaton starts in some initial states, and at any given point, it is in its particular state. It reads the letter, it gets a set of possible states, it chooses one of them, non-deterministically, it guesses one, and it continues, and it has to make the right set of guesses, so the final set is accepting. Here is a little example, a little automaton that have two states. We can call them left and right. You enter on the left, and 0 always take you to the left, and 1 always take you to the right. And the red circle tell you what is you accept on the right. So if you look at it, you realize that to accept, you simply have to end with the letter 1. So this defines the language of all the words that end with 1. And we know that NFA defines a class of regular languages, which is very, very robust class, and has many, many nice properties. So this class was introduced roughly mid-50s, around the mid-50s. And then very quickly people realized that you can think of any word as a mathematical structure. What is a mathematical structure? A mathematical structure has to have a domain and a set of relations. So if you have a word of length n, then the domain is simply the set of positions in the word, so it's a set 0 to n minus 1. And the relations are the inequality relation that tells you the order between position, and monadic predicates that tell you what letters are written in each position. So P sub A holds at a point if the letter A is in at that point. And now using these atomic formulas, the monadic and the inequality, you can write sentences. Here is a sentence. It says there exists some x, such that for all y, not y bigger than x. So we tell you that x must be the rightmost position, because nothing is to its right, and P sub A of x. So the letter A is written at x. And in fact, you can go even further and talk about monadic second-order logic on words by allowing quantification over sets of positions. Okay, and I won't, for lack of time, I won't give an example. And the fundamental result, proved independently by Bushy, Elgot, and Trachtenbrot almost about the same time, is that these two very different formalisms, NFA on one hand, automata, and logic, MSO, they have the same expressive power. They both define the class of regular languages. And the proof is constructive. You go back and forth. If you start from an automaton, you can build a sentence that describes exactly the semantic of this automaton. And more interesting from our point of view, if you start from a sentence, you can build an equivalent automaton. And the construction described in these papers in the late 50s was by induction on the structure of the formula. You start from atomic formula, and they correspond to some very simple little automata. And then you have to show closure under the logical operation. So you have to show closure under this junction, and that corresponds to union. And you should remember that regular languages are closed under union. And you have essential quantification, and that corresponds to projections. And you may not remember what is projection, not important, but again, you should remember maybe that regular languages are closed under projection. And finally, negation corresponds to complementation. Okay? And if you look at the complexity of this operation, so because we're dealing with non-deterministic automata, union is very easy, and projection is very easy, they're all linear time blow up, but complementation requires that we do the subset construction, and that blows up the size of the automaton exponentially. Now I want to move to decision problem. So for automata, the most fundamental decision problem, there sits right here in front. For automata, the most fundamental decision problem, given automaton, does it accept any word? Okay, is it empty or non-empty? Is the language non-empty? The language is empty, it's a very boring automaton. And it's very easy to see if you go back to this picture, the reason that there is some word that is accepted is because you can walk from initial to accepting states. There is a path from initial to accepting states, and that turns out to be really the condition that you need. You can define the graph of the automaton, which you simply obtain by erasing the labels. So the graph of the automaton is a directed graph, the nodes are the set of states, and you have an edge from S to T, if it's possible to make some transition from S to T. And it's a very easy exercise, it's an undergraduate level exercise to say the automaton is non-empty if and only if in this graph there is a path from initial to accepting states. And so you see that this can be checked very easily. This is the most fundamental graph theoretic problem, reachability. You can use breadth first search, depth first search, and you can solve it very easily. Linear time in the size of the graph. Now the corresponding problem for logic is a satisfiability problem. Given a sentence, does it have a model? Is a set of models non-empty? And on the face of it, if you look at the sentence, it's complicated, alternation of quantifiers. It's not clear how you even start to answer such question. But the translation to automata gives us an algorithm, right? Because it's very clear, because the automata and the sentence are equivalent. They describe the same language. Therefore, the sentence is satisfiable if and only if the automaton is non-empty. So this is the algorithm. Translate the sentence to an automaton, and then check non-emptiness of the automaton. And the second step, we already know, it's linear time. So the only question is, what is the translation? And now you go back to this beautiful inductive proof, and you realize that one of the inductive steps is exponential, and you may have to iterate it many times, and that means that you actually have a tower of exponentials of unbounded height, of linear height. And the first thought is, surely I was just not smart enough. I took the most straightforward algorithm. If I just spend another 5 minutes to think about it, I'll come up with a better algorithm. But nobody could come up with a better algorithm. And eventually, about 15 years later, Stockmeyer was able to show there is no better algorithm. This problem is really non-elementary, even for first-order logic already. Okay, there is no bound, there's no fixed bound on the tower of exponentials. Now, around the same time, Alonso Church, who usually you associate him with recursion theory and lambda calculus, gets interested, I don't know exactly how, in circuit design. Okay? And he's studying a model. The notation has matured a little bit since the 50s. Today we call it sequential circuits, and it's a very fundamental model, less in computer science and more in electrical engineering. Anybody takes a course in digital design, this is the universal Turing machine. Okay? This is the model that models every piece of hardware, because nobody really has an infinite tape. Everything is finite state. And it's an input-output machine. It's what you're also, if you may remember, it's called a transducer, but it's simply encoded everything is binary. So we have a set of input signals. All the signals are, again, Boolean signals, 0 and 1. And we have a set of output signals. And we have a set of register. Every register is simply a 1-bit memory. And the logic of the circuit is described by two Boolean functions. One that looks at the current input assignment and the current register assignment, the current memory assignment, and it tells you what is the next memory assignment. So this is how you change the state. The state is the memory assignment. And the other function is the output function. Given a current memory assignment, register assignment tells you what is the output. And you have one initial state. These are the initial assignment to the registers. Now, such a circuit requires to be driven by a sequence of outputs, and then you give it one input, and then you give it another set of inputs, and so you get an infinite trace. And so this is a trace, every element in the trace is a triple input, register, output, and it has to satisfy the obvious equations, which is that all the transitions of the memory corresponding to the function f, and the output always behave according to the function O. And so this is, as I said, this is a classical description of what we call sequential circuits, as opposed to combinational circuits. They have no state. They only give you input and output of one step, essentially. Now, again, Church realized that you can think of an infinite trace as a mathematical structure. Remember, a mathematical structure has a domain. Here, the domain will be simply the natural numbers, and we'll have, again, binary relation, inequality to compare time points. And every circuit element, input signal, output signal, register, is viewed as a monadic predicate, because at any given time point, it is a true or false. So this is exactly what the predicate is. At any given, for every element, it is a true or false. So you get first-order logic from this. And here is an example of a sentence we can say in first-order logic. We can say, for all x, there exists y, such that y is greater than x, and p holds at y. And if you think what this means, it means that p must hold infinitely often. Okay? This is the only way you can always go to the future and find a point where p holds. And again, we can go to second-order logic if you allow us to quantify over sets of points in time. And that gives you additional expressive power. And then Church poses an amazing problem, and is exactly what we call today model checking. Except he didn't yet use the term at the time. He called it the decision problem. What is the model checking problem? Given such a circuit, there are infinitely many possible traces, depending, of course, on the input, what input is going to drive the circuit. And suppose you have a formula, a sentence in MSO that describe legal traces. So you'd like to know, given a circuit, is it the case that in all possible traces, the specification holds, the requirement holds? Okay? This is exactly what we discovered later as model checking. Now, Church was not very interested in complexity, so he made the obvious observation. You can reduce it to satisfiability by encoding the function f and g in first-order logic and combining it with the specification. Okay? He did not solve the problem. He posed it in a talk in 1957. And then it was solved by Richard Bushi, who I believe was Swiss. And he took automata theory that was defined in the 50s and extended it to infinite words. Now, the extension does not require any change in the format of what is an automaton. If you look at the definition of Bushi automaton, you see it. I just changed the label, but it's exactly the same object, right? It's a tuple. It has a finite set of states, a finite alphabet, a non-deterministic transition function, and a set of accepting states. And the only difference now we feed it an infinite sequence of letters, because it's an automaton on infinite words. So we feed it an infinite sequence of letters, and what we get out is an infinite run. So unlike automaton finite words, where we have a clear decision point, the automaton finish, it has to announce, I accept, I reject. Here the automaton runs forever. So Bushi proposed a mathematical definition of acceptance. You say you accept if you visit accepting states infinitely often. So if we go back to the same little automaton, where you enter on the left, you go to the left with 0, you go to the right with 1. Now, to go to the accepting states infinitely often, you have to see infinitely many ones. So this automaton defines the language of all the words that contains infinitely many ones. Now, as I said, you're all familiar with the class of regular languages, which is very robust. So already in 1960, people realized there is another class of omega words, and this is called the omega regular class of omega languages. And it shares many of the nice properties. It has many closure properties of the regular class, but it is less familiar, but somehow it didn't make its way into the textbook as an undergraduate material. But it's a very robust class of omega languages. Now, Bushi again proved that there is an intimate connection between the automata theoretic view and the logical view. And essentially, they are equivalent. And I will only state here the more useful theorem from our point of view, which is the theorem that takes you from logic to automata. And I'll call it the compilation theorem, because to me, this is an application of a very fundamental idea in computer science that really was discovered in the 50s, that humans work better at the high-level languages and machine work better at the low-level languages, and we bridge the gap by computers doing the compilation. Okay? So the compilation theorem tells us that you can start from an MSO formula on infinite words, and you can translate it to an equivalent automaton. And because you have such a translation, again, you can solve the satisfiability problem. It means that you have to solve the non-emptiness problem for Bushy automata. So if you remember, for NFA, non-emptiness meant that there is a path from initial to accepting states. Bushy automata require infinitely many visits to an accepting states. So the lemma would tell you that automaton is non-empty if there is a path from initial to accepting states and then a cycle back to the same state. Okay, so you can think of it as, depending on whatever your imagination, either as a lollipop or as a lasso. Okay? In Texas, we call it lasso. And so essentially, Church proved that satisfiability of MSO over omega words is decidable, and Church is very happy. And it's interesting that in his talk, he mumbled something, something about the complexity. I don't even necessarily use the word complexity because that was yet a standard term. But he realized that this is not a very efficient algorithm. And of course, we know by Stockmeyer later that this is non-elementary as well. So we have nice decidability result, but there is issue of non-elementariness. And even though for finite words, non-elementariness has not proved to be a barrier, there was some of the work done here, reducing actually the package model, reducing it to practice. For omega word, it is still a serious barrier. And there is really no good really practical implementation of this whole theory on omega words. Now we jump to the end of the world, to Christchurch, New Zealand. Probably I think it's maybe the most southern city. And we meet Arthur Norman Pryon, who is a philosopher that is occupied also with religion. Throughout his life, he made some changes. He was born a Methodist, converted to Presbyterian, then he became an atheist. Before he died, just to be on the safe side, became an agnostic. And he was concerned on ethics. He wrote a book, Logic and the Basis of Ethics. And if you think about logic and religion and ethics, you have one colossal problem, which is the problem of free will. Okay? So to have moral responsibility, I must be a free agent. I must be making free choices. If I'm just a puppet, I'm not responsible, right? Nobody thinks about a coffee machine and think that it's morally responsible if the coffee didn't come out good because the buttons were not pressed correctly. And so on one hand, we all believe that we have free will, but some religious doctrines, I think Methodism, actually believe in what's called predestination. Whatever happens has already predestined, predetermined. But then it's not clear why we have any moral responsibility. So there is an attempt to reconcile this, and it says, yes, God knows everything. But you have free choice, but God knows what you're going to choose. Now you have to think, okay, does it make sense that I have free choice, but God knows what I'm going to choose? So Pryor was very concerned for that, and he realized, okay, to think more precisely about these issues, you need a logic of time. So he goes and develops what became known later as temporal logic. At early time, it was called tense logic. And there is an interview with his wife after he died. He died somewhat early in his 60s, and his wife recalled, I remember he's waking me up one night in 1953, coming and sitting on my bed and saying he thought one could make a formalized tense logic. He was excited enough that he would go and wake up his wife. I have a new logic. I find it's very endearing. In 1957, he publishes a book, Time and Modality, and this is the beginning really of the modern era from, if you are a temporal logician, this is where the big bang, so to speak. Now, as soon as you start thinking about temporal logic, you run into one thorny issue: what is the underlying nature of time? So when Pryor started talking about it and lecturing, and in the book, he thinks of time as something very simple. Time unfolds. Time unfolds, so it's a line. It's just an unfolding of history. But then in September 1958, he gets a letter from Sol Kripke, one of the foremost philosophers of the 20th century. And Kripke writes thusly: in an indeterminate system, we perhaps should not regard time as a linear series as you have done. Given the present moment, there are several possibilities for what the next moment may be like. And for each possible next moment, there are several possibilities for the moment after that. Thus, the situation takes the form not of a linear sequence, but of a tree. Now, of course, the amazing thing is this was not Sol Kripke, the foremost philosopher of the 20th century. This was Sol Kripke, a high school student in Omaha, Nebraska. Okay? So some people are precautious. So that means that we have to make a choice between these two views of time. Is time is it just a line, things just unfold, or do we have a tree, as Kripke suggested? Now, Prior was interested in free will. So it's not just about what you do, but what you could do and you didn't do. So really, the branching time is more attractive if you're thinking about this. It's not so easy today to figure out what really Prior had in mind, because when you try to read the book, you run into formulas like this. I mean, I had to copy it character by character because I have no idea what it means. And they didn't have good fonts, so they didn't use like symbols we use today, arrow, wedge, things like that. Everything was a Roman letter, and they really loved Polish notation. Anybody here from Poland? Maybe they can read it. Okay? I cannot read it. But here is what Burgess says about 20 years later. Prior would agree that determinist sees time as a line, and the indeterminist sees time as a system of forking paths, a tree. And we will see this issue will come back. Now, even if you accept that you need branching time, it's philosophically very delicate. Prior believed that time is branching, but the course of event is linear because it's just one thing after the other. But Rescher says, no, time is linear, and the course of event is branching. We have branching in time, not branching of time. Is that clear? Because I don't understand it. I don't know really what it means. And I even asked a co-author of Rescher, what did he mean? And nobody can explain to me what he meant. But some people just ignore this whole branching time and continue to study linear time. They thought it was interesting enough. And then in 1968, Hans Kamp proved a fantastic theorem. He finally said, what is the relationship between this new logic discovered by philosophers and classical logic, first-order logic? And he proved that if you enrich, until then, people Prior only use like always and eventually, and Kamp introduced binary temporal connectives, since and until. And he proved that with this enrichment, you look, for example, over the integers, and first-order logic is exactly the same expressive power as temporal logic. Okay? So very nice connection between this new logic and classical logic. Now, already the philosopher realized that there must be some connections to computer science. Even though these guys know very little about computer science, they're speculating there are some connection to computer science. And then, in 1977, Amir Pnoeli gets interested in a very modern aspect of verification, which is what happens if you have programs that don't just take data, compute, and produce output, but they just run forever. Okay, so classical verification was about input-output verification. And now, already then, people realize some systems just run forever, so we must have a language to talk about ongoing behavior. And he tried first-order logic. He had a paper with Nissim Fazez in 1975 on first-order logic, and he wasn't very happy. And it's an interesting story that I don't have time to say, how he discovered temporal logic, developed by philosopher. And he said, oh, this is perfect, this is the right logic. And he wrote a paper in 1977 that ultimately he received the Turing Award for this paper that proposed using temporal logic as a logic for reasoning about ongoing behavior. And he even discussed model checking in that paper. And he proved that it is decidable. And by, for example, by using, again, by reduction to MSO. And it was non-elementary, but he was really thinking more about deductive verification, so the non-elementariness, again, did not bother him too much. So here is the logic that Pnoeli introduced. And again, it evolved a little bit from the first paper to future papers, but I will ignore now. This is a bit historically inaccurate, what I'm writing here. But essentially, you start from propositional logic, and you add temporal connective. And what are the temporal connective? You can say something is always, something is true in the next time moment. You assume the time is discrete, tick-tock, tick-tock, so you can talk about the next moment. And you can talk about what happens eventually and what is true always. And the binary connective introduced by Kamp, which is phi until psi. And here you see in the picture the description. This is the next. So something is true here. Next phi is true here. if phi is true in the next time moment. And the until is phi until psi means phi until at some point psi is true. So let's see a couple of examples. So specification in computer science usually follow what the sumist told us, which is depart from evil, this is safety property, and do good, and this is Leibniz properties. So you can say always not critical section 1 in critical section 2. It means two processes cannot be in a critical section at the same time, and this is safety. And two Leibniz property always requires implies eventually grant, or always request implies that request must stay on until eventually grant. So this is, of course, a slight difference in what is the request grant discipline, and here you can very precisely say what is the proper discipline. And this paper has been incredibly influential. I don't know exactly, I need to check, but it has thousands of citations, I'm sure. Pnoeli wanted to know the expressive power of this language, and he was interested in a slight reformulation of the concept of expressive power, so he couldn't quite use camp result as is. So he recruited some logicians, Gabay, Shelach, and Stavi, and they reproved camp theorem in a slightly different setting, but essentially it's the same expressive power that LTA is equivalent to first-order logic. Now, interestingly, a couple of years earlier, Wolfgang Thomas looked at what is the expressive power of first-order logic over omega words, and he proved that they're equivalent to star-free omega regular expression. So you're all familiar with regular expression over finite words. There is a version of it which are called omega regular expression, and if you drop the star, you get star-free omega regular expressions. So now we understand that it's a hierarchy with two levels. At the bottom level, we have LTL, which is first-order logic, and the star-free omega regular expression. And the level above it, it's MSO, which is fully omega regular. You have all omega regular languages there. Now, in 1980, Albert Meyer gives a talk called 10,001 Logics of Programming. And the talk is mostly by dynamic logic, which we're going to see in a minute. And he ends by talking about temporal logic, which he completely puts down. He's very dismissive of temporal logic, linear temporal logic. And the reason is because he referred to the GPSS, that's what we call it, the GPSS 80 theorem. And he said it's equivalent to first-order logic. So who cares? Why do we need another logic? It's equivalent to first-order logic. What I find amazing in this is that he missed a crucial difference. We know that first-order logic, already assumed by Stockmeyer, is non-elementary. The complexity is non-elementary for satisfiability. So now you have a different logic with the same expressive power. You can ask, how does it behave computationally? And the answer is, and it was shown by several people in the next couple of years, that LTL behaves very differently. It is very, very elementary. It is in p-space. And for logic, p-space is a new polynomial time, essentially. Okay? This is very, very tractable if you're doing logic, p-space complete. And the basic technique used by all these people to prove that it is in p-space is a tableau technique. Tableau technique is a technique that came from modal logic, and we'll see in a minute how it came to computer science. So LTL and first-order logic are equivalent from expressive point of view, but very, very different behavior computationally. Now, a couple of years later, Pnoeli, with two students, realized that Hans Kamp also had the past. Do you need the past? So it turns out from expressiveness point of view, you don't need the past. Now, what is the past? For every temporal connective, you have the dual one that look back. So all the connective look forward, and the past look backward. So if you have next, talk about the next point in time. Yesterday looks at the previous moment in time. And past means something was true sometimes in the past, or always in the past. And since, so you can have a dual connective, and you can say a very useful thing. You can say always receive implies past sent. If something has been received, it must have been sent before, right? There's no, messages do not appear out of thin air. They must have been sent before. So Pnoeli and his students prove, first of all, that you don't get more expressiveness, and they prove that you don't get more complexity. Now, only later, Nicolas Marquis was able to show, however, that you get a logic exponentially more succinct. So this is, if you can think, this is a free lunch theorem, right? Tell you have a logic that is exponentially more succinct, but you don't pay you don't pay a cost when you're going to do satisfiability. And Pnoeli and his students argued that this is a very useful logic because you can specify certain properties in a very natural way. If you try to take the same property and you try to satisfy it in future temporal logic, it's much more awkward. So they argued in favor of past temporal logic. Now, the other, I would say, if you look at our field, there was a huge, the paper by Pnoel in 1977 was a big bang in some sense. And then in the early 80s, you have two papers, one in Europe, one in the United States, introducing modal logic for a logic that is called CTL, computational tree logic, and we'll see what it is in a minute. And this was a branching time logic. And Pnoeli again felt that he needs to respond because he actually liked better linear time. So for CTL, model checking is linear in both the program, which means the state space of the program, and the formula. And for LTL, it's still linear in the program, but it's exponential in the formula. But Pnoeli argued that formulas are typically short, and therefore you can live with exponential with the size of the formula. Again, he uses tableau. So at this point, you seem to have somehow a tension. Do you use the more mathematical elegant theory of MSO and automata, but that costs you a non-elementary blow-up? Or do you use this set of heuristic called tableau, and then you get something which is more efficient, it's only exponential. So at that point, for a few years, it looks like you have to have a choice between, in some sense, being rich and being beautiful. But then Pierre Wolper and I were able to show that this is not the case, and that there is an exponential compilation theorem for LTL. And so you can compile LTL formulas to automata with precisely, at most, an exponential blow-up. And so you don't do this inductive translation, but you use some kind of a global translation, and you get an exponential translation. And then once you have the exponential translation, all the other results, such as satisfiability and model checking with optimal complexity, they fall out from the exponential compilation theorem. And a few years later, I was able to show that this is the case even with the past. You still have exponential compilation. So even though the logic is exponentially more succinct, when you go to automata, you don't pay any cost, okay? It is still exponential. And there was, the next decade was an effort to reduce things to practice. And by the mid-90s, we had at least two systems that implement LTL model checking. One was spin by Gerard Holtzman that did explicit state, and one was SMV by Ken McMillan that did it with symbolic techniques. Now, Alonso Church dies around the time, around 1995. So I always imagined a conversation I would have on his deathbed. And I would say, well, you remember your model checking problem from 1957? Not only we solve it, but we actually have systems that implement it. And just before he died, he would have said, not quite, because you're doing LTL and it's only first order logic, and it's not fully omega regular, and I was interested in MSO, which is fully omega regular, so you still are not quite done. And then he dies. So indeed, throughout the 80s, we wanted to see, can we enhance LTL to make it fully omega regular and still get the same complexity results? And by the end of the decade, essentially, we had two answers. You can do it in two ways. One is you put automata inside the logic. This was a logic that proposed originally by Pierre Wolper in his PhD dissertation. Or you can put fixed point, like mu calculus, linear mu calculus. You can put fixed point quantifier, so to speak, inside LTL. Either way, you get full omega regularity, and you can do it still in p-space. So theoretically, we had a good answer, and we were satisfied. Now, remember, temporal logic came from philosophy. Another logic came from philosophy into computer science, almost about the same time, completely independently. This is one of these cosmic confluence. Things happen about the same time. And this is dynamic logic, which was introduced by by von Pratt and brought into computer science. And essentially, he takes the box modality of modal logic that says necessarily, and he reinterprets it to mean after one step of the program, then he opens the box and puts the program inside. So box alpha phi means phi holds after the execution of all executions of alpha, and this matches very nicely whole logic. And there is some very intensive investigation that comes out of it. So one is von Pratt discovered tableau techniques for modal logic and bring it to computer science. Everybody learned about tableau from von Pratt, who read everything there is to learn about modal logic. The other idea that comes out of it, modal logic is, dynamic logic is branching time. So computer science rediscovered branching time in some sense here, due to von Pratt. And thirdly, there is a question that arises: what is a propositional program? And Fisher and Lander proposed to take regular expressions as a way to think of what is a propositional program. A propositional program is just a regular expression. So the ideas that we get from here are tableau and branching time and regular expressions. So the computer scientists now are completely unaware of the debate that took place in the 60s, late 50s and 60s among philosophers, whether time is branching or linear. And they reinvent the wheel. And again, they say, okay, and start promoting branching time and linear time. And one big innovation that comes out of it is that Prior did not, even when he adopted branching time, if you look at branching time, you have a problem. When you talk about the future, there are many futures. Which future are you talking about? And so Prior had a very complex way to do this. And actually, Ben-Ari, Mann, and Pnoli proposed using explicit quantifiers over future. So that's how you get the logic CTL. You must quantify over the future, either universally or existentially. You have to say in all futures, you have to say there exists a future. So this is an idea that Prior somehow missed, that you need to quantify over the future explicitly. So by the mid-80s, again, we have this big debate between the proponents of LTL, where you look at time as a line, and you say things like always request, eventually grant, or you have branching time, where you always must quantify over the future. And there is this debate, but there's no way to settle the debate. So after a while, out of exhaustion, it just becomes a draw. Nobody knows how to settle this debate. But one thing that people try to do is to try to always, we have two logics, can we unify them, can we combine them? And again, a lot of papers, but I'm going to jump to the late 90s. And what happened in the late 90s, that a group at IBM in Haifa decides to borrow the regular expressions that we saw in dynamic logic and put them into CTL. And out of this, they get a logic by 2001 that they call sugar, which is essentially CTL enhanced with regular expressions. Okay? So now industry is using some mixture of temporal logic and regular expressions. Now, Intel started playing with model checking around 1990. Bob Kurshan was on sabbatical in Technion in Israel, and he was very close to Intel, and he got involved with some project at Intel. He was able to find some very critical bugs in the cache coherence protocol, and Intel decided to invest in model checking, and they developed even their own specific property specification language. A group of engineers sat together, develop a language, and if you've ever seen a language developed by a group of engineers, you can imagine it's very ad hoc, just let's throw a bunch of features together. So that was the language. And then they decided they need to have a second generation of all the tools, so they built a new generation of model checkers, and they decided also they need a new language. Decided the old language was very kludgy. They decided they need a new language, and eventually this became the language ForSpec, and I was invited to join that project. So I went to visit them in 1997 to consult with them about languages for specifying properties of hardware. And I first proposed LTL. I said, nice, simple logic, very simple semantics, easy to understand. And they said, no, it's not expressive enough. Now, this to me was kind of a revelation because I was convinced that expressiveness is an issue of theoreticians. And so when they said it's not expressive, they didn't mean, well, it's too weak because it's not expressive, it's not equivalent to MSO. They couldn't care less about MSO. What they meant was, we cannot say the thing that we need to say in this logic. Okay? It's really too weak. Cannot specify hardware. So, of course, I was thrilled because I had the papers that were from a decade earlier, and I was pulling out all papers. I said, look, you can solve it, you can introduce automata, or you can put fixed point quantifiers. And they said, no, I mean, we have to understand, we have verification engineers. These are people with just bachelor degree. We cannot talk to them with all these fancy concepts, okay? So we ended the year in a stalemate, but I came back a year later. At this point, I knew that I have no chance with even trying to sell them fixed points. Forget about it, okay? Nobody will buy fixed points. But I thought I can convince them to put automata in the language. And they still said no. But then Avner Landwehr, who worked with me, asked me, because he knew about what IBM has done, he asked me, what about regular expressions? And I said, you don't know? They're equivalent to automata. He said, really? I said, yes, I can show you in the book. So I said, you mean that automatas in the language are bad, but regular expressions are good? He said, yes, people love regular expressions. So I said, yeah, let's shake hands, we have a deal. So we basically took the dynamic modalities of PDL, of propositional dynamic logic, and put them inside LTL. So you get things like box E-phi. So here's an example. Box, true star, so this sequence of true, so it's arbitrary sequence, and then send, and then not cancel. So if you see a trace that has send, not cancel, then in the next cycle, it must be a send. So if you send, you push the send button, you have one cycle to change your mind and cancel it, and then it's going to be sent. Okay, property you can save. And because it's equivalent to automata, we can prove that this is fully omega regular. Okay, it's fairly straightforward. This was already known before. And so ForSpec is really this language, RE-LTL. LTL was regular expression, plus a variety of hardware features that are all syntactic sugar for engineers, okay, which I won't get into. So I'll try to speed up because we're running out of time. Around 2000, a process started of trying to industrialize and have standards for the industry wanted to have a standard temporal logic. So a standard committee was put together, and they got donation from 4 companies, from IBM, Intel, Motorola, and Vericity. Vericity since had been bought by Cadence. And IBM was a branching time logic, and all the other companies used linear time logic. So the first thing the standard committee has to do is to debate the merit of branching versus linear time. So now you remember the debate before whether we have branching in time or branching off time. Now imagine this debate happening by industrial standard committee. And if it sounds surrealistic to you, it was. So the outcome was this weird compromise where IBM won politically because they had more votes on the standard committee. But the compromise was they had to make sugar a linear time language. So at the end, PSL, which is what emerged, is a standard property specification language. It's essentially ForSpec, but this became nominally IBM won the contest there. And another standard came out of it, which is SVA, System Verilog Assertion, and the boss today are IEEE standards, and they help push the model checking in the hardware industry. Now, remember that I mentioned before this by Lichtenstein, Pnoli, and Zook, this work about the past. They argue that the past is very useful. It turned out that people in the industry were not very interested in the past. And when I tried to understand why, they said, look, you have a circuit. Anything that's in the past that is important must be remembered by the circuit. There must be some register in the circuit that remembers that. So it's become the past becomes the present, right? The past is important only if you remember it. And so it's become the present in some sense. When you talk about the past, we're talking about the present in our memory. So this was the argument. But this argument only is correct if you already have the hardware in front of you. But if you want to think what happens earlier, when I just want to start specifying the system and I want to specify them using linear properties, then I need the past because it was shown to be very useful. So around 2010, Dak, Slatke, and Lang, and also Luker and Sanchez, argue that we need the past and they want to enhance the past. So for example, RTL is a logic proposed by Dak, Slatke, and Lang, and they start with past LTL, and then they add the dynamic modalities. But for every dynamic modality that looks forward, they have a past modality that looks backward. And they prove the same, what I call free lunch theorem, which is that the language is expressively equivalent to LTL with regular expressions. It is exponentially more succinct, but you pay no penalty in complexity. And I like this approach, but I think it can be simplified. So I'd like to pose a logic which I'll call that linear dynamic logic, LDL. And this will be simply the dynamic modalities. First of all, you don't need the temporal connective, but because they're all subsumed by the dynamic modalities. For example, if you want to say always Q, it's the same as saying box true star Q. So you can think of the temporal connective as syntactic sugar. The other thing that you need to do is for every letter, have a reverse letter. And what is the meaning of the reverse letter? It means go backward in time. And in fact, already PDL, dynamic logic, had reverse operators because you needed both to think about a strongest post-condition, which goes forward, and weakest precondition that goes backwards. So already Pratt introduced this reverse operator. And if you're familiar with XML and XPath, you also have a concept of reverse navigation going up an axis, and also you use the converse of a letter. So now we can say, if we remember what we want to say before the past, now I can say box true star receive, diamond true minus star send. If at some point you see receive, then you must be able to go backwards and find that that message was sent earlier. And you get a language that is equivalent to RELTL, exponentially more succinct, and still p-space complete. So why did we like LTL so much? It was simple semantics, linear time, simple syntax, exponential compilation property, and equivalence to first-order logic. So let's look at LDL. It's linear time semantics, very simple syntax, just regular expression with reverse. It has exponential compilation property, and it's probably more expressive. It's equivalent to MSO. Also in American English, and I'm not very good at doing it, but maybe some American can do it here, there's not much difference between T and D. Okay? If I say Adam, it's not clear, am I talking about Eve's husband, or am I talking about an indivisible particle? Right? It sounds the same. So if I say LDL, you cannot even tell whether I'm talking about linear temporal logic or linear dynamic logic. Thank you very much. No, general expressivity, everything. Yeah.
The exponential,
Yeah.
But actually, I think general adding the history engineering, and this has been.
Yeah.
It really is the right thing, and people don't understand Congress.
We are saying people don't understand the past, and I'm not sure I would agree with that. I think all of us use the past extensively, and so far, in fact, if we have trouble, usually it's with the future and less with the past. So I don't quite agree with your assertion that people don't understand the converse. But you're conflating two different things here. One is the issue of the underlying logic, is it temporal logic or the dynamic logic? And the argument is and essentially the industry has already gone to dynamic logic. So the industry is between both PSL and SVA have regular expression. So that debate has already been settled in some sense by the industry. And the only question is about do we need the past? And you said, well, you just have to add history variables. We want to start thinking about the behavior of the system before we add history variables. And so to say a message a message received must have been sent, you might implement it later by adding a history variable.
Ghost history variable.
Well, but that's essentially, the ghost history variable is essentially if I said sometime in the past it has been sent, this is equivalent to saying there is a ghost history variable here. So it's a way to capture ghost history variable inside the logic rather than force you to have a different addition on the side. Thank you very much.